tackled yet in some depth is really the role of technology in Society 5.0, because it's critical. We've talked about systems, we've talked about form and function, we talked about stakeholders, we talked about life cycle properties, we talked about architectural decisions, but we haven't really talked about technologies yet. And it's an important topic because technologies are the embodiment of form and function. And technologies, of course, evolve over time, which is what I want to talk to you about. And new technologies might change the rank ordering of the architectures that Brian just showed you on the multi-dimensional charts. And so an architecture might be very good for a particular technology, but when that technology is getting older and maybe less competitive, a different architecture might be the preferred architecture. Now, if the system is not evolvable or not adaptable, it is, we say the system is locked in. And we do have some systems in society that are locked in to old architectures that if we were to design the system fresh from scratch today, we would actually pick a different architecture than we picked, some years ago when it looked like the best option. So that's really what I want to talk to you now about, is how do we think about technology life cycles? And then hopefully everything will really fit together logically in your mind, how all these concepts relate to each other. So when we think about technological progress over time, there's a lot of discussion on it. It's in the news every day. We talk about it in universities, in companies, but the essence of it is that models of technological progress, there aren't that many. There are many different technologies, but there are not that many ways to think about how to model technological progress. And what I would say to you is, I think there are three ways to do it, three different models. And initially, these models may seem at odds with each other, or that you have to pick one of them. But at the end of this lecture, I will hopefully convince you that no, in fact, these models are quite compatible, complementary to each other. And that's the S-curve model, the Moore's law, and then the Pareto shift. So you can see, in this case, we plot performance or any of the other figures of merit that you're interested in over time. And here we plot the logarithm, so the log of performance over time. And in the Pareto shift model, we plot different figures of merit against each other, and time becomes implicit. And so the discussion we just had on airplanes, and one of the reasons why the A380 is being retired is because the Pareto front of technologies has shifted and now made it an inferior choice if you were to buy a new set of airplanes. So the S-curve model, the basic idea is that in the S-curve model, that new technologies initially, when they're immature, when they're just being invented, are initially slow due to lack of knowledge and experience. So this is the left part of this curve. But then at some point, the technology will progress quite rapidly in the middle of its life cycle. And as the technology matures and gets older, and the low-hanging fruit of improvement has been harvested, progress will slow, and eventually you get diminishing returns. And so it's actually possible to formulate this mathematically. So this is one of the possible ways of getting an S-curve mathematically. This is the famous logistics function. And so I just picked here some random parameters just to show it conceptually what it looks like. And so A, B, and C essentially show you it essentially stretches the curve either in the X or Y axis, and then especially tau will determine how slow or quickly the transition from an immature to a mature technology will occur. And we have given names to these different stages of technology maturation. So we might have an initial proof of concept, and then we have an incubation period, very slow progress. Then we have takeoff. The technology starts to improve much more rapidly. Rapid progress in the middle of the life cycle. We have a slowing, and then eventually we have stagnation. One thing that's also quite important to understand, and I think people in general or organizations don't think enough about theoretical limits. These are limits imposed on us by physics, by chemistry, by biology. And so the closer you get to that theoretical limit with a technology, the harder and harder you have to work to get any improvement. And that's the main reason why we see stagnation. So I want to do a little bit, I want to ask you a question which I've asked other groups before. And so your answers will be added to the answers here. I list a set of technologies here. So the internal combustion engine, laser communications, and so forth, all the way down to RNA interference. And what I'd like to have is your opinion. Where do you think in its life cycle on the S-curve this particular technology falls? So if you would please go to this link, tiny.cc/S-curve, and respond to that. And so I give you maybe 20, 30 seconds to respond to this, and then we'll go and look at the responses. tiny.cc/S-curve. And Brian, I don't know if you want to put this link in the chat maybe as well. Just make sure it doesn't have the S for HTTPS. It's just HTTP. Could you do that? Thank you. All right, so let's go and see. Okay, we see we're getting responses, which is good.
Can you share the URL again, please?
Can you see the responses on my screen?
I can see the responses, but we didn't share the URL.
I see. So it's HTTP. Let me go back here for a second.
Just tiny.cc/S.
Tiny.cc/S-curve, lowercase. Is that okay?
Yes.
Thank you. All right, so we have some responses. Let's go look at the summary. All right, so the internal combustion engine, we have the majority thinks that we're in a stagnation phase, that essentially the internal combustion engine is quite mature and it's stagnating. But there's some group that says we're still improving it, which I think is true, but at a slower pace than we did, 10, 20, 30 years ago. So it's quite mature. And in fact, we now see a substitution with electric motors. Next technology, optical laser communication. This is used on Earth. It's also used in space. And so this is in the rapid progress stage. I would agree with that. It's still not a mainstream technology, but it's being increasingly matured and used, for example, for intersatellite links. I think, I don't know if Shirasaka Sensei, are you with us today? I believe there is also some research happening at Keio University on laser communication or optical communication for Shinkansen, for providing very high-speed internet connection during train rides using optical communication. So rapid progress. DNA sequencing, for sure. I would say if we had asked this question 10 or 20 years ago, most of you would have said it's just taking off, but it's definitely progressing quite rapidly. Quantum computing, the majority of you said it's in the incubation phase. I think that's correct. Robotically assisted surgery. So this is, for example, the Da Vinci robot is used for some kinds of surgery, but not all. So it's somewhere between takeoff and rapid progress. Unmanned aerial vehicles, UAVs, drones for various purposes are making rapid progress. And then RNA interference, which is a new technology in the life sciences to not just fight diseases, but suppress diseases from expressing themselves in the first place. And so definitely RNA interference is very new and still in the incubation phase. So, you know, this is the kind of wisdom of the crowds. And I find these results quite interesting, and they confirm, I think, a lot of my own understanding of where these technologies are. So I hope you found this to be useful. Now, what's interesting is when you ask for, or when you go looking for examples of actual S-curve data in different publications, you find very little. The school in the management literature in business schools, there's a lot of discussion of S-curves, but there's very little evidence that they actually exist. So here is one of the best examples that I can show you of actual data of that shows S-curve like behavior, and this is a chart that's updated, regularly by NREL in the United States. This is the National Renewable Energy Laboratory, and what it shows is the efficiency of solar cells. So photovoltaic cells converting photons into electrons, into electrical current. And the different colors show you different types of solar cells. So multi-junction in purple, they're the most efficient. Crystalline silicon cells, those are the majority that we can buy commercially. You can see they're less efficient, in the range of 20%, 25%. Thin film technologies, which are quite new, and then emerging PV, including organic cells, quantum dot cells. We're just at the beginning here. The world record, by the way, is 47%, which is for a 6-junction cell with 143x solar concentration. So it's quite, and you will find several Japanese organizations on this chart as well, since like Sanyo, for example, on the silicon cells, Japan is very, very active in this field. And you see that, for example, for the multi-junction cells, for the silicon cells in particular, we have periods of progress and periods of saturation, but the real S-curves are not as smooth and clean as the theory suggests. Nevertheless, we can use this data both for fitting, this curve here is discrete. So you can see these discrete steps. And I'm just showing you the data for triple junction solar cells here. So what we can do is we can approximate the rate of technological progress using a kind of smoothed equation, the S-curve essentially. So we fit the S-curve using a least squares approximation, which gives us those 6 parameters you saw in the equation as a best fit. And now we can use that also for prediction. Prediction is always challenging and always dangerous, particularly if you do linear extrapolation. But if it's a nonlinear extrapolation, taking into account theoretical fundamental limits, it can be quite useful. In fact, you can see here that the blue curve is a prediction of how the essentially the best multi-junction solar cells will perform in terms of efficiency. And you see that the current world record in 2020 is quite close to what the model would predict. And you can see this diminishing returns that we talked about already. Another model beside the S-curve is Moore's law, very famous. Moore was actually one of the co-founders of Intel, and he wrote a paper in the 60s observing that the density of transistors doubled about every 18 months or so. And so this is showing you the transistor count versus year, and each of the dots here represents a particular processor. And notice that it's a logarithmic chart. So we can approximate it, and I just picked a few of the processors. We can approximate it in log space as a linear curve, and it fits quite well. Some people have said that Moore's law is finished. It's no longer valid. It's saturating. I see no evidence of that. I don't think there's any real evidence that Moore's law is no longer valid. So the simplest way to write down Moore's law is that the performance of your system, or the figure of merit that in this case we care about, is equal to Y naught, which is the performance at some reference year, for example, 1970, times 1 plus R to the T. R is, of course, the annual rate, or the average annual rate of improvement. And so for computing, for processors, that number is an astounding 37% per year. And it has been 37% per year, as you can see, for the last 50 years or so. And so that's absolutely remarkable. And the way that it was maintained, if you go back to this chart, is to see that we went from single core to multi-core processors. So modularization, parallelization allowed us to stay on this curve. So this number R, the average annual rate of progress, is really important, and it's essentially the same as your bank account, the interest rates in your bank account. A 1% difference in savings, in rate of return on your investment or your savings, accumulated over time, can make a very large difference. So just to show you here generically, if your technology improves at 2.5% per year, after 30 years, you will have doubled your performance. If it's 5% per year, it'll be about 4 times. And if it's 10% per year improvement, it's about a factor of 15. And if it's 37% per year, as we see here, well, then it's, 10 orders of magnitude or more. So each percent improvement per year difference makes a huge impact over the long term. Here's one of my favorite examples, which is Moore's law applied to timekeeping. I think this is, I've mentioned timekeeping several times, and I know this is a passion for accuracy and precision that Japan shares as well. So what this shows you is different clocks or timekeeping mechanisms over a period of about 1,000 years. And so the amazing number here is that we keep improving our ability to keep time at a rate of about 1.8% per year, but now over 1,000 years. And so you might ask, what is this figure of merit? The figure of merit that I defined here it's the drift of the clock. So it's how much does the clock deviate from true time over some amount of time. So how many seconds per week or per year does the clock deviate from true time, divided by the volume of the clock. Obviously, if you have a lot of volume available, it's easier to make a precise clock than if you have a small volume available. So it's a normalized metric. that I call timekeeping accuracy. And what's also interesting is that when we look across this, this curve, the particular concept, the way that Brian explained it, the function is the same, keeping time, but the concept and the embodiment has changed. We went from sundials to mechanical clocks, to quartz clocks, to atomic clocks, and now we're discussing, in fact, implementing quantum clocks, which are even more accurate than atomic clocks. So I think I'm going to have to update this chart. So timekeeping has improved about 1.8% over the last 1,000 years. And then here again, we have evidence of progress in computing, a slightly different metric, not transistor count, but MIPS, millions of instructions per second per US dollar. And we get about 31% per year. So it's a slightly different figure of merit, but the number is very similar to what we saw with the classical Moore's law. So effectively, Moore's law doesn't just apply to transistors or processors, it applies to all technologies. But what is different is what is the slope of the improvement, the rate of improvement. And so here you see some additional examples like electric motors. You see MRI, which is magnetic resonance imaging. So electric motors improve about 3% per year, and that's on the figure of merit of watts per liter, so power density. And MRI improves about 20% per year based on resolution over time. And in fact, there has been research done by some of my colleagues, such as Professor Chris McGee here at MIT, looking at the rate of progress for different technologies. And so you can look at this list here, which is quite impressive. And what I did is I just highlighted those technologies that I think are close to the core mission of IPA and DADC, like optical communication, wireless telecom, semiconductor memory, CT scanning, IC processors. And you can see that they're all on the left side of this chart. They're all progressing at increasingly, at very impressive rates above 20% per year. And so when you're designing and thinking about Society 5.0 and future-proof architectures, the fact that these technologies are improving about 20% or more per year has to be factored into your considerations. Some of the more, let's say, mechanical or electromechanical or energy-intensive technologies like batteries, electric motors, they're also improving, but they're improving, at a rate that's, say, below 10% per year. And then the third model, like I mentioned, is the Pareto shift. So the example that Brian discussed with the automobiles, acceleration versus price, would be of the left kind, so smaller is better. So the utopia point is in the lower left corner. And so over time, each of these lines, this is time t plus 1, progress is from the upper right to the lower left. Or if your figures of merit are of the larger is better kind, then these Pareto lines, Pareto curve, will shift from the lower left to the upper right. And here's an example of that from aviation. So this is the progress in aircraft engines in terms of core thermal efficiency and core propulsive or mechanical efficiency. So the thermal efficiency is how efficiently do you convert the energy in the fuel, in the kerosene, to hot air? And the propulsive transmission efficiency is how efficiently do you convert the hot air in the combustion chamber to forward thrust that's propelling the aircraft. And so you can see that one of the original engines, the Whittle engine in the UK, was here, a very poor overall efficiency, only about 10%. And then we've improved dramatically in recent decades. And we keep improving further with new architecture, like unducted fans, for example. So I just want to, and how do we do this? Well, we do it with better materials, architectural changes, for example, going from 1 stage to 2 stages to 3 stages, optimizing the geometry and other design improvements. And so here I want to show you one of the examples of, I think, a very impressive engine, which is the GE90. And there's a new version of it, the GE9X, currently under development for the Boeing 777X aircraft. These engines are very large, they're extremely impressive, and 2 of those engines will power a very large airplane. And that was not the case, 15 years ago when you needed 4 engines. And that's one of the primary reasons why the A380 is currently no longer competitive in the market. So the point I'm trying to make here is that as technology progresses, there comes a point where the technology has improved so much that a new or different architecture becomes the preferred choice, the dominant architecture, and will replace the incumbent architecture. And so if we try to bring it all together, if you think about it, we talked about the S-curves. The classic model for a single technology is the S-curve model, and there's really some evidence that S-curves are real. Few theoretical limits exist, mainly those based on physics. And so the S-curve model predicts some kind of saturation. However, we saw that progress in functional performance is exponential. And so one of the fundamental questions, and maybe I just, pause here, or you could respond in the chat, isn't there a fundamental conflict between these 2 models? The S-curve model says that we have saturation, but Moore's law says there's no saturation, and we keep making exponential progress. So isn't one of these must be correct and the other one must be wrong? Or what's going on here? So if you have any thought on this, if you would put that in the chat, please. And Brian, if you could help me out to see if there's any responses.
S-curve is based on using the same architecture.
Any other thoughts?
Not yet.
I think, okay, that I would agree with that statement. So here's the solution to the puzzle. No, there is no conflict. Why not? Because we are switching to new technologies or new architectures. So the way you can think of it is that we have each technology is on an S-curve, but it's the particular form, the particular embodiment that is on an S-curve, not the functional view of the technology. So new technologies come in. Initially, they are perhaps inferior, but once they hit the rapid progression stage and the old technology is in the saturation stage, there will be a crossover point. That's the key. And this can happen not just once, this can happen multiple times. And so what we get is these, what I call interlocking S-curves. And when you look at it in the aggregate, it starts to look like a straight line, like an exponential progress. So the S-curve and Moore's law are not in conflict. They in fact are complementary to each other. And to kind of illustrate this, I'm giving you examples from these 3 domains that we discussed. Computing, we went from mechanical computers to solid-state relays, transistors, ICs, and I think it's a very interesting, and Brian, since you graduated in computer science,
I did.
And so maybe you have an opinion. What is the future of computing after integrated circuits? Is it optical, so photonics? Is it biological computing using DNA, or quantum computing? Do we know?
So from we were seeing all the hints right now that both have to do with scale. And scale, as we've gone beyond Moore's law, which was based on a certain physics, if you will, we're now at a point of scale where the physics changes. So that's quite interesting. But the other key aspect, of course, is both quantum and distribution. So all three of them actually require a change in the concept of computer. And so I think the biggest jump here is going to be specifically driven by quantum, not by the others. So we have to train a whole new generation on how to so-called program.
Yeah, yeah. So I think we don't quite know yet, but it's happening. It's really happening. And I don't know the time horizon of Society 5.0, but maybe this will be relevant for Society 5.0. What kind of computers will we have? How will they change, computing, data storage, algorithms? This could be very fundamental. In transportation and propulsion, of course, we have seen the transition from the piston engine to the turbojet to the turbofan to hybrid electric propulsion. And so also here, I think we have a big question mark, hydrogen. So when I was at Airbus, we decided to join the Hydrogen Council. And the idea is that hydrogen could replace kerosene as the fuel of choice for large aircraft. Not everybody believes that, but certainly it's worth exploring. And here I will also say that Japan, without a question, is one of the global leader in the hydrogen economy. I'm very aware of the Toyota Mirai, for example. I'm aware that Japan has, it's still small, but one of the world's leading number of hydrogen refueling stations. So this is something also to consider, is what is the role of hydrogen in Society 5.0? And then we talked about timekeeping. So going from sundials to mechanical clocks to quartz to atomic, and perhaps to quantum clocks in the future. So the summary is that there's more questions here than answers, I think. So I'm just going to pose some of these questions. Do we ever really retire technologies? I still have vinyl records, the old turntable records. And so I still use it and I really enjoy it. And there's a revival of vinyl, actually. Can we predict the crossover time between an old and a new technology? Do functions that improve at a higher annual rate, so this is the slope of the Moore's law, see more frequent technology transitions? What ratio of rate of improvement of old and new technology and performance can inform optimal R&D investments and timing? And this is something that I thought a lot about, particularly in industry, is how to optimally allocate R&D budget between maturing or further improving mature technologies versus investing in newer ones that are just at the beginning of their S-curve. And then the big question for this workshop is, how do new technologies enable architectural innovation? So the good news is that there will be an exercise. There will be two exercises this afternoon. One will be on analyzing an existing system and the life cycle properties. Dr. Shingo Kawai. Shingo, are you with us?
Yes, I'm here.
Thank you. Shingo, do you want to explain the first workshop, which is not about technology specifically, but about life cycle properties? And you can do it in Japanese. It's okay.
Thank you. 皆様はじめまして。本日午後のワークショップでは、IoT を、ベースとしましたですね、スマートファクトリーのエクササイズというのが3つ目。4つ目には、e コマースのエクササイズがあります。で、 従来の工場に比べてスマートファクトリーと呼ばれるようなものではどういったテクノロジーが使われるのかとか、あるいは今日、講義にありましたイリティーズの話というようなことを皆さんにですね、ちょっとディスカッションしていただこうと思っております。よろしくお願いいたします。Is that all right, Ali? Okay, I will give baton to you.
Thank you very much. And do we also have Fukatsu-san? Takeshi, are you with us as well?
Yes, I'm here.
I think you're going to be leading the fourth one, right?
Yep.
Do you want to explain?
はい。今回4番目のエクササイズで、取り組むのは e コマースのテクノロジーについてのアーキテクチャを作ろうと考えております。でこの e コマースというのは、例えば Amazon とか、アリババとか、最近店舗物理的な店舗に代わって、こういった電子商取引が流行ってきていると。でその成長率もすごいことになっているんですが、そのケーススタディを行う中で、アーキテクチャ、どういったアーキテクチャが今後プロスペクティブなのかというのを皆さんにで一緒に考えるというワークショップを考えております。よろしいでしょうか。Is that all right?
ありがとうございます。Thank you to both of you. This was excellent. And so, yeah, so this brings us to the end, I think, of the lectures of day 2. We covered, you have to be aware that the topics that Brian and I covered in these last 2 days, we gave you an extremely fast, high concentrated dose of these ideas. Usually we spend more time, more exercises, and there's more time for you to absorb. So, but it's okay. Our goal here is to expose you to these ideas, and I'm sure there will be other opportunities for you to also think about it and apply this. So please return this afternoon for these exercises. It will really help you to work together to make these ideas become more real, and also more real in the context of Society 5.0. So I wanted to see if there's any other questions at this point.
Based on the understanding of technology life cycles, how could an architecture consider future progress of core technologies, which is rarely predictable? In what case should an architecture change?
Okay, so the very important consideration here is when you look at different architectures and you look at the functional decomposition of the system, right? Which system provides what function? So, for example, if it's a data acquisition system, you will have sensors, you will have parts of the system that does signal processing, amplifying signals, cleaning up signals, filtering them. You will have a part of your system that will do the computing, like fast Fourier transform, things like that. And so each block of your system, if you think the system should live for a long time, you need to modularize the system in a way that you are allowing yourself to keep the slower moving technologies in place for a longer time. And those technologies that move very fast and that might be replaced quickly, that you can drop in, substitute a new technology without having to retire the entire system, so that the slower moving technologies can continue to exist or coexist, and the new technology is inserted. But this is only possible if you thought about it ahead of time, and if you've chosen an architecture that is modular to allow this kind of technology upgrading. If the architecture is very kind of monolithic or connected, you can't do that very easily, or it would be very expensive. And in that case, often you need to retire the entire system and replace it altogether. Does that make sense?
Yes, the answer is yes. Thank you for your answer.
Okay. Thank you very much. And so we wish you a